It occurred to me the other day that my young son will never know a day before voice control. I mean, I talk to things all the time, and they listen and respond accordingly. Well, most of the time. No, Alexa, I said order a pack of 4D batteries, not 4T batteries. That's going to weigh like 500 pounds. Wonder how much shipping's going to be on that. Well, when I was a kid, people that talked to inanimate objects, that was something else entirely. The center of all of this voice activated everything is deep learning. And maybe you're thinking, hey, I'd like to try my hand at some of this deep learning business. Well, step this way, my friend. Hi, I'm Amelia Dalton, host of Chalk Talk. I know a lot of you are going to be super excited about this. I know I was too. Today, we are going to talk about how you can get started with a deep learning project with MATLAB. Please welcome Girish Venkataramani from MathWorks, who is going to talk about all of this and more. And before we get started, don't forget to click that link. There you can find more information about deep learning with MATLAB. Welcome, Girish. Thank you so much for joining me.
Pleasure being here, Amelia.
Okay, so I'm ready for some serious deep learning. What are we talking about today?
Right, so deep learning is this new phenomena which is kind of sweeping our world today. And it's a subfield of machine learning. So actually, if you think about it, neural networks are a way to do machine learning. And what a neural network is, it tries to emulate the structure of our nervous system. So we have neurons in our bodies, and the neurons kind of decide what kind of signals to let through the network and what reaches the brain, and then the brain reacts. So the neural network is designed to emulate that system. So each layer in a network is emulating a bunch of neurons, and it decides what kind of information can pass through the network. And by doing so, it's actually performing some kind of a function.
Sure.
And so deep learning is a kind of neural network. It's a specific type of neural network.
Okay, so a lot of deep learning is about vision, seeing things, identifying things. But how exactly does that work?
Yeah, so deep learning really took off with the computer vision and image processing area. So let's take an example. So let's say that when we look at that picture on the left, we know it's a flower. So how does a network decide it's a flower?
Yeah.
So the way it does it is by a series of steps. So the network itself is deep in that it's got a lot of layers. And the initial layers are responsible to just kind of find primitive features in the image. So things like edges and corners. And it's just trying to figure out where these things are.
Okay.
As we go down the network, the middle layers are putting these primitive features together to form shapes. So we have rectangles, squares, and other kind of polygonal shapes. And then finally, towards the end of the network, these shapes, they come together to identify objects. So at this point, we have identified features which represent certain objects. So the deep learning network is really a feature extractor in that sense. So it's extracting features from our images. And then finally, the last few layers are what we call classification layers. And they are trying to classify the features that we have just detected so that we can come up and say that this is a flower.
Sure. Okay. So somebody told me that there has been more progress in AI in the last couple years than in all of history before that. So what's new in the deep learning arena?
Yeah, so deep learning itself, it really came into prominence in the last, I would say, about 5 or 6 years. Before that, we've always had machine learning, and machine learning has been a popular technique for building computer intelligence. Mm-hmm. So the big difference between machine learning and deep learning is that with machine learning, somebody had to do the feature extraction part manually, so outside of the network. So there were all these really advanced algorithms which were proposed in the computer vision area to kind of find features. Feature extraction is a big field of research in itself. So you'd find those features, and the machine learning networks themselves were just shallow, and all they were doing is classification, and we could just tell if it's a flower or not a flower.
Yeah.
What changed with deep learning is that these networks now got much deeper, and the feature extraction is now automatic. It's part of the network. So network itself decides what features to extract. And this became quite reliable. The difficulty has always been that with deep learning, it requires a lot of computation power.
Sure.
And to train a network, you need a lot of data.
Right.
Guess what? Today, we got the web. We got trillions and terabytes and petabytes of images and data, which you can train the networks with. And we got a lot of compute power too. So that's why it's become very popular.
Okay, so I've already accepted that computers and robots are coming to take my job. But what kind of jobs will they be able to do?
Yeah, that's a good question. All I can tell you is that, well, deep learning really started with the field of vision, but it is trying to emulate the way that we perceive things. So it is kind of enabling human-like perception. So it started with vision, but there's already a lot of research which allows us to identify speech, natural language processing. Facebook, Google, they're already using these techniques to understand kind of the search terms that you put in, for example.
Sure.
And then text, again, once you put speech and text together, you can do quite a lot of things. So where will it take us? We don't know. We'll have to wait and see. But the technology enables us to kind of give these things like Alexa and Siri a lot more intelligence than they had maybe 3 years back.
Okay. Girish, let's dive into MATLAB. How do we design our deep learning app using MATLAB?
Great question. So you need to build your network. First thing you need to do is design a neural network, which is designed to do the thing that you need to do.
Okay.
And as I mentioned, deep learning networks are created only when they can be trained with a lot of data. So you need to have a lot of data available, which means where do you store this data? How do you manage this data? And also during the training phase, you kind of have labeled data. So it basically means that you know the result. Right? You already know what this image is, and you're training the network and seeing if it picks the right answer.
Sure.
If it doesn't pick the right answer, then you go back and fix certain things in your network. And that's what the training process is. So with MATLAB, this task of managing your large data set and labeling your data, which is a pretty huge problem. Think of petabytes of images, and you want to go in and say, this is a dog, that's a cat. How do you do that? So we have a lot of tools which enable you to manage the data, label it, and make it easy to access it. And once you have that, then there is the training. And MATLAB provides all the algorithms which are necessary to train a network, and it's pretty straightforward. You provide the data and you provide the goal of your network, and MATLAB can train it not only just on your machine, but it can also push the computation out to the cloud. So say Amazon AWS systems, we can scale to clusters of computers and make sure that the training runs fast. Because remember, training can take days.
Yeah.
So you really need a lot of compute power. You need to do that really fast.
Absolutely.
Yeah. So that's the first thing. So first you train the network. So now you get a trained network, which you're kind of happy with its performance in terms of what it's identifying and whether it's doing the task that you intended it to do. Now, you could train everything in MATLAB, but the truth is there's a lot of frameworks out there which will enable you to build deep learning networks. So Caffe is one of the first ones which was out in the market. So this is coming from University of Berkeley. They have a pretty rich set of models that they've trained. And then TensorFlow is from Google. They've built a framework which can also train networks similarly. So we don't limit our users to using MATLAB alone. So we also provide model importers which can convert your Caffe models and TensorFlow models into our MATLAB environment. So you can bring your networks that you've already pre-trained into MATLAB. Now, why would you like to do that? Well, once you train the network, that's just a network. It's just doing one thing, right?
Right.
You need to build an application which is using that network. And that's the next step, which is application design. So if you got your training, application design means that you're using the network to do a particular task. And I'm going to show you some examples later on. The idea is that there is going to be more logic that you need to write around the network to actually achieve your goals.
Yeah.
And that's easy to do in MATLAB. And that's one of the benefits of being in the MATLAB environments, bringing your networks into the MATLAB environment. So finally, once you've finished building your application, then you might want to deploy it. And what does deployment mean? You might want to run it on, let's say, a drone or on your phone or some other kind of device, on one of your IoT devices. And so you need to deploy it, which means those smaller devices might have less memory. It might have a very stringent performance requirement. And we need to be able to meet those requirements when we deploy these networks. And remember, these networks can be really large and quite computationally intensive.
Yeah.
So that's why in MATLAB, we have a new product which was released last year called GPU Coder, which allows you to generate code automatically from these networks to what is called CUDA. CUDA is a language which is used by GPUs. GPUs are graphical processing units, and they are predominantly used for deep learning. And so with GPU Coder, you can get really high performance, low memory footprint of your generated code, which you can then deploy onto your device.
Okay, I understand that deep learning requires some serious compute power, but Girish, how do we get that?
Yeah, that's a good question. So, like I said, there's these devices called GPUs, and GPUs stand for graphic processing units, right? So GPUs actually started with the gaming industry back in the 90s, right? There was like NVIDIA had their GPUs, and AMD and had their GPUs. And what was special about GPU is that you can think of it as there is a processor updating every pixel on your screen. And so there's a lot of parallel processing going on, and that's why it was so great for rendering and display and gaming.
Sure.
However, they figured out eventually that, well, you know what? There's a lot of processing power here, and you can just use it for general purpose compute. So that's where GPUs really took off. And with deep learning, you need a lot of compute power. So GPUs really stepped in and took on that challenge. And today, they're easily an order of magnitude faster than CPUs. So that's where you get a lot of your compute power. And so deep learning is being enabled by these devices.
All right, Girish, am I going to have to crank out billions of lines of code to make all this happen?
Hopefully not.
Oh, phew.
So the good news is that with MATLAB, building a deep learning application is really straightforward. So we got a lot of examples. Here's a link to a video which is online where my colleague Joe is talking about how you can easily take an idea and build a deep learning application around it with just about 11 lines of MATLAB code.
Nice. Okay. All right. Let's dive into some applications now.
Yeah. Sure. So I'm going to first talk about deep learning is becoming really important with autonomous driving. So
Sure.
A lot of these problems, you can't sit there and write if-else conditions. If there's a pedestrian in front of me, do this and that. So
Right.
you need to make it much more autonomous, right? Like much more seamless. So it's been used in a lot of different kinds of perception problems, as they call. So things like figuring out what's in our environment.
Yeah.
So this is one of those problems. Where are the lanes that I'm going to be driving my car on? That's a common problem. So this problem is about detecting lanes in a scene, right? And you got to do that fast because the car needs to react really quickly.
Right.
So there are typically 3 phases in the deep learning application design. So as I mentioned before, first you collect your data, then you train your network, build your application, and deploy it. And
Right.
I'm going to walk through some of that.
Okay, so Girish, how does deep learning keep my car in its lane? Can it do it better than my dad? Because seriously, he's kind of scary sometimes.
Yeah. All right. So the first thing we need to do is train this network so we can actually identify the lanes, right?
Sure.
So as I mentioned, you need to label your data. And this is kind of a pretty hard thing to do because think about it. You have to train it perhaps with millions of miles of driving videos, right?
Right.
And you need to go in there and with every frame of the video, you need to mark the lanes so that you can train the network saying this is where the lanes are. You hopefully can detect this.
Yeah.
So with MATLAB, we have a tool which allows you to do this automatically. So this comes in a tool called Automated Driving Toolbox. And what it does is you can go into each frame and manually first mark the lanes. So you can draw lines, rectangles, polygons, and whatnot, and put labels on them. So by doing that, you're labeling your data set.
Right.
Now, the nice thing about this is in addition to doing that, so that's how it works. So you go in there, draw boxes, draw lines, mark the cars, mark the lanes. But you can see that this can be quite brain numbing eventually, right?
Yeah.
You're doing this in every frame of the video.
Absolutely.
So we have a way to automate this. So there's something called a point tracker. So you label one frame and say automatically label the rest of the frames. Just track this object. So
Nice.
you can specify a number of frames or a time limit, and MATLAB will automatically label the rest of the frames, which really makes it easier. So then now we got our labeled data, right? So next task is to train the network. Here comes some of the more innovative ideas of how do we build a lane detection network. So in this particular approach, what we did is we defined the lane as a parabola. Right? So let's say it's ax squared plus bx plus c. So if I want to know the shape of the lane, I have to figure out what are the coefficients of my parabola, a, b, and c. A common approach in deep learning is to take an existing network and retrain it, when we call this process transfer learning, to a new network. Because remember, I initially mentioned that a lot of deep learning is feature extraction, right? The classification part is in the end. If you're classifying a different problem, you can still use most of that feature extraction stuff. It can be still common. So that's quite a common approach. So we took a well-known network called AlexNet and transfer learned it to detect lanes in my image. So outcomes of this network, 6 outputs, which are 3 coefficients for my left lane and 3 coefficients for my right lane. Once I find the coefficients, I know where my lane is. Then I have a better idea. We actually published this in a blog on NVIDIA's site, and you can learn more about it there.
Nice.
And finally, of course, now, how do I use it? So I now have figured out the coefficients, but now I need to tell my car to say, keep in the lane, right? Let's not get out of the lane. So in order to do that, I need to have a better understanding in my image where this lane is. So I just know the coefficients right now. So I need to do some post-processing so that I convert these coefficients to the pixel coordinate space. So there's some more work involved after my deep learning network has done its job. So when I deploy this is my application design, right? It's both a network and some glue logic. And so when I deploy this, I want code for the entire thing, not just my network. As what GPU Coder allows us to do. So let's look at how this happens. So this is my algorithm in MATLAB. I first have a network, my lane detection network. I'm calling prediction on my network, and that's basically going to give me my coefficients. So I got my coefficients, that's all it took. The rest of the code is basically converting from that coefficient space to the coordinate space. So with MATLAB, I can test this very easily. So I have a test file which brings in a video, and for each frame of my video, I'm calling my algorithm to see if I can see the results of my algorithm. So you can see what the video looks like. That's the input video, right? So we're going to run it in our test, and this is running just in MATLAB. And you can see that it's doing a pretty good job of marking the lanes, and it's running pretty fast with 90 frames per second just running it in MATLAB. But of course, if I want to deploy it in a car, I need to generate code, and that code needs to run maybe even faster because it's a smaller device. GPU Coder allows you to generate code automatically. So once you generate code, we now have C CUDA code, which is not just MATLAB, and you can take that C and CUDA code and put it on the computer in your car. And it'll run in the car. So we're just now testing the generated code, and you can see it's running a lot faster than just MATLAB, and that's what we want. So the generated code needs to run really fast for us to respond to the changes in the lanes and the environment.
Okay, so Girish, are there subtasks that we train that are part of bigger tasks? And then is there a hierarchy involved?
Yeah, that happens quite often. So here's another example, again from automated driving. And this example is trying to identify traffic signs in the image. And here there are 2 problems. So it's not just classifying the image itself, the whole image. There could be multiple traffic signs in my image. I need to find all of them. I need to know the exact location of those traffic signs, and I need to know what each traffic sign is.
Right.
So we break this problem down into 2 networks here. So we first have an object detection network, which is looking for traffic sign. It doesn't care what the traffic sign is. We just need the coordinates of the traffic sign. Once we find that, we do some logic after that to kind of clean up the results. And then we have a second network, which is called the classifier DNN, which actually is telling us what type of traffic sign is in each of these boxes.
Right.
And so that's what this application does. So I have another example here. I can train my network in MATLAB, as I mentioned already. And the training, here's an example of the few lines of code. managing your data is easy with the data store abstraction, which is provided in MATLAB. That's how you create your network. You specify what types of layers you want. A lot of it is pretty standard. You have a few convolution layers for your feature extraction and fully connected layers for your classification. And then finally, you run training. So that's the options we provide to our training, certain parameters, and then we train the network. We got two networks. We got a classification network and our detection network. Now we can build our algorithm. So this is the application design part. And in our algorithm right now, you'll notice that we have two networks. So we have first the detection network, whose whole job is to find the bounding box coordinates where the traffic signs are. And we get those results, and then we convert it to attributes that we can then further use in our algorithm. So it is basically taking the results and massaging it to a form which is more understandable for the rest of the algorithm. So we do that, and finally, there is some cleanup going on. We call this non-max suppression. But finally, once we get all of this cleaned up data, then we can run the second network on it, which is doing the recognition. So you can see there's a loop there. So it's for each of our bounding boxes, we're trying to figure out what's inside that traffic sign. Once again, with MATLAB, it's very easy to test this. So I have a video here, which is a driving scene, and I'm basically trying to find traffic signs in each of the frames. And I'm also trying to compute how fast my algorithm is running. So again, I can just run this in MATLAB to see how well it does. So MATLAB is an environment that is very nice for testing. So you can see it's doing a pretty good job of finding the traffic signs, labeling it correctly. Our performance is at about 25 frames per second. Pretty good again with just pure MATLAB. But once again, if you generate code, you can get much higher performance. And that's our goal, that we can generate code and put it in our edge device, in this case, a car. So we are using an API to generate GPU code. And once this is done, I'm actually going to show you a little bit of what this code looks like. So this is C CUDA code. So it's not MATLAB anymore, right? So that's why we can deploy it. And if you look deeper into the code, so that's the top level function of our generated code. And first thing you'll notice is that there is a lot of stuff going on besides just our deep learning. So there's a deep learning inference, but there's also all this additional parallel kernels, we call them CUDA kernels, which are generated to make your application run faster.
Yeah, okay.
So now we're going to test this. We got our generated code. I'm going to call the generated code directly from MATLAB, and we have a way of doing that. So we can test how well the generated code works. So once again, testing it on the same video, you can see that it's doing the right thing and it's running a lot faster.
Excellent. All right, so let's talk about benchmarking. How does the performance of using MATLAB compare with other approaches?
Yeah, so that's one of the areas we put special focus on. Our goal is to be one of the best performing frameworks. So here is a comparison of how MATLAB and GPU Coder compare with a few other frameworks. These are quite popular frameworks, MXNet, Caffe2, and TensorFlow. And these are running on a GPU called Titan XP. And you can see here, this is for the inference performance. This means when I put the train network in the car, how fast is it running?
Yeah.
Right, that's what we are trying to figure out. And with GPU Coder, you can get about 7x higher performance than TensorFlow, 5x faster than Caffe, about 2x faster than MXNet.
Nice, okay. So I think I'm ready to get started. How can I get me some deep learning?
Of course. There's a lot of resources available on the MathWorks side.
Excellent.
So first off, there's a landing page called Deep Learning in MATLAB. You can definitely check that out for all the resources that you'll need. But the link at the bottom there, the Deep Learning on-ramp, is really useful. It's a free 2-hour self-paced training which anybody can access. You just need a MathWorks account. It's free. And you can learn more about deep learning and how you do it in MATLAB.
Very fun.
And once you're ready, you can also use GPU Coder to deploy your code and get that high performance.
Excellent. Well, I think that's all I have time for today. Thank you, Girish. This was super cool.
Thank you. Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find more information about deep learning with MATLAB from MathWorks. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal or check out YouTube, keyword EE Journal.